Good morning, I'm JK.Han from Robotics and Mechanism Lab at Virginia Tech. Today I will be providing more details about the DARwIN-OP hardware. So there are several features built into mechanical design that makes it exciting for a number of different applications. At first, it's very easy to work with, easy to disassemble and replace components due to its modularity. A big part of this modularity is built into dynamics and motors. Kim already introduced about the motors. Dynamics have a variety of mounting points, output configurations, and are electronically linked with both power and communication signals through daisy chain wires. I think you already know about the daisy chains. In addition to its modular design, DARwIN-OP's center of mass is located at the right hip joint, which can simplify the model and simulation. It's also designed and built to meet our local rules for the key side division of the humanoid leg. Therefore, it is ready for the competition right out of the box. And one more thing is the computational. Sorry about it. Excuse me. Computational platform in DARwIN is based on conventional PC platform. Therefore, it has all the features most PC users are used to, including DVI, USB, and Ethernet, and camera, speaker ports, as well as all the computational power necessary for local competition, as well as a research program. The last one, the most exciting feature is on its open platform design, which makes it very easily modified by any user. Meaning it's easily hackable on both software and hardware level. Therefore, many additional features can be added. For example, a gripper can be utilized by modifying the code. I will talk about it later. So, as I mentioned, DARwIN is designed to comply with all the rules of the key side division of the humanoid leg of the local software competition. So, if you want to compete in the local competition, this robot meets all the criteria as it is purchased. Some of the key requirements are it must have a humanoid form. I'm going to explain about the humanoid legs rules briefly. So it must have a humanoid form and locomotion strategy. So the robot cannot use leg and arm to work, something like that, like this. It's illegal. And its size is also very important. So we are focusing on the key size leg. Key size is the smallest size, and it's most exciting game as long as it. At the height of about 46 centimeters, it qualifies as a key size robot. Another important dimension is the foot size. Everybody knows how important foot size is, which directly affects the stability of the robot, as well as being closely regulated. The rule stipulates that the foot area should be less than the height squared by 30. It's a little bit confused, but this number means it should be up to more than 100 eventually, but they are using 30 now. So that Darwin robot fit into that 30. And then one of the most thing is the arm. The arm are also specifically designed to have a span less than 1.2 times of the height. We're still allowing the robot to stand up after it falls. You already watched how awesome the stand-up motion. Therefore, if anyone wants to participate in the future robot competition in the humanoid league, they can just bring the robot without any modification. Yeah, that's it. Okay. Next, I want to introduce about the range of motion of Darwin. These column shows the standard human's range of motion. Please compare to these two guys. This is DARwIN-OP's range of motion. Of course, Darwin doesn't have waist and some other things, but it's good enough to mimic the human motion, and the range is very similar or more than human beings. For you, I want to talk about the field of view. The next slide. The field of view for Darwin is very large when one considers both the camera field and the range of motion of the head. This gives DARwIN-OP the ability to track the object. I want to show you how camera cover the area. So this angle is a range of motion of the head, and this angle is a range of ROM, and this shape is camera field of view, camera itself. So it can cover from minus 80 degree to 60 degree, and it can in the top view, the Darwin can cover from more than minus 105 degree to plus 185 degrees. Which means you can see everywhere. Honestly, the local rules is slightly less than this degree, but dynamics model can cover this degree, so you might need to make it small to attend the competition. Anyway, for another reason, you can use all of them. That's the ability of Darwin.
In the lens we focus background?
Yeah, we are using a USB HD camera. The model number is what's the model? C905. Right? Logitech camera. Yeah. So.
Okay, oh, that's very good.
Yeah, it has autofocus. Right? Autofocus is manual.
So also, as I mentioned, it's an open platform, so if you want to use a different type of USB camera, take it out, put it in, so you can modify it.
Yeah, I want to talk about the modifying later, the last slide. So anyway, it's one of the features of DARwIN-OP. You can disassemble anything you want and assemble anything, any sensor, some cameras, and something like that. So I'm going to talk about it later. So next, I will introduce how to assemble the Darwin and something like that. So the Darwin assembly can be divided up into 5 main modules: legs, and arm, and lower body, how can I say, the hip group, and upper body group, and electronics modules. In this picture, you can see how easy it is to disassemble sub-components from each other with a modular design and gauge chain wiring. This gives users the ability to quickly and readily assemble, disassemble, or replace a component. The main concept of the hardware design is modularity. So you can modify one of those. You can, if you want another arm, you can take this guy off and you can assemble your own hand or arm or leg. That's the main concept of the hardware design. So let me introduce some more. Video. Here, the following video, you can see a stop motion movie. The first process takes approximately 5 to 6 hours and is done with all M2 hex bolt or Phillips head bolt. As you can see, the modular design makes it easy to assemble with simple hand tools and more resembles putting together an electro set than a humanoid robot. Here you can see the assembly process. So I just take one guy off from the assembly manuals. I want to show you the legs module for one example. So this is a foot and hip joint. So you can start from the one motor. So from this, you can attach some brackets, for example, foot, something like that, and keep assembling, assembling brackets like this and like this, and connect the wires like that. You can see it needs just one wire because it uses gauge chain. So it's very simple components. It uses very simple components. So next, yes. And of course the process for assembling the other 4 modules is similar, like this, similar. And let's go to the electronic part. The electronics are composed of only 2 powerful components. One is the primary PC, which is this, called PPC, and that is responsible for the high computational performance of DARwIN-OP, and is used for the high-level controls and programming. This PC has all the normal features user will expect, such as USB, DVI, and Ethernet ports. For low-level control and sensor hardware uses the CM730 from Robotics, which is this board. This board integrates all sensors necessary for working, such as IMU. Both these components are arranged in the chest. This is a chest. It's fit into this area. That consumes very little space and maintains a lower proportion. And is an improvement. I think it's an improvement over the customary backpack solution. So most robots has a backpack for computer or battery also, but it's one of the different points with another robot. Next, I want to talk about the cases. You see the three designs of the DARwIN. There are 14 different injection mold parts available as case for DARwIN-OP. These parts are not necessary for the robot work, but are available for sale from robots. The cases are precision molded out of polycarbonate, which is the material often used for its impact robustness and toughness. The injection molding process allowed for the part to be made very precisely, thus reducing the overall thickness and therefore weight of the robot. Because the material is also very strong, it is resilient to bomb and force. As you can see, the Vice President kicked the robot, but it was okay. Thanks to the polycarbonate. You know what the window, bulletproof window is made by this polycarbonate.
So is he bulletproof?
Like a robot.
Will there be other corruption?
Sorry?
Will there be other corruption?
Color options.
Color? Okay, you can paint it.
By the way, seriously, we expect a lot of people to make their own covers at Show Off because all the CAD files are available. I'm sure a lot of people are going to come up with really deep looking covers.
Yeah, that's true. Okay, I want to talk cover more. DARwIN-OP with cover is capable of enduring the rigors of Robocop soccer game. But the cases can also be made to interact with one another. Therefore, the case go together very nicely, such that the seam can almost not be seen. You can see the robot. Could you watch the robot? You cannot see the seam in here and here, things like that. Yeah. You cannot see it because we use the injection molding part. And let's talk about the CAD model.
About it, off the record, the DARwIN-OP, the head design, is modeled after a particular person in this room. Yes.
I want to say who he is. Oh, he or she is.
Quiz, right?
Do you have another gift?
We're going to do one right after his
Okay, all right.
Good.
I'll shut up.
Okay, let's talk about the CAD model. As we have been emphasizing, DARwIN-OP is a model for an open source platform, and that extends to the 3D models. Therefore, if you use any 3D CAD package, such as Inventor, Pro Engineer, or CATIA, for example, you will be able to download either a file in STEP or IGS format. We will provide the two kinds of extension style, so that import them into your CAD software. This gives users the ability to design new parts to interface with the robot. As I mentioned, you can take the arm off and assemble your own design. For example, Michael designed his head for his robot. You brought your head, right?
Your head?
The robot's head, not his.
I often confuse with robot and people. And something like that. So that's one of the big advantages of DARwIN-OP. In addition, anyone wishing to actually fabricate a robot from the ground up would be able to do so from the CAD file. I usually use ProE to design the robot. It's the capture feature of my computer. You can import it like that, import the robot like that. Then after they purchase the motor and electronics, they will have a complete robot. In addition, in the case of failure or accident, user will have the option of fabricating or repairing of replacement part to specification. Okay, next. Let's talk about the academic area. As we have been emphasizing, DARwIN-OP is a model from open source platform, and that extends to this kind of reverse kinematics and dynamics. Making the mechanical design openly available. So we will also be providing additional information that would be useful in developing kinematics and dynamic models of Darwin. We're gonna open this solution. This solution is for 6 degrees of freedom lag. So the target of this is solve the inverse kinematics for lag. You can use this equation for your class or some analyzing your research and project and robots. So what's that? The theta, these guys are joint angle. If you put the position here, here, you can solve the appropriate joint angle of each motors. And also we will explain how we get to there. For example, from the some metrics and some equations. And also we will provide the physical properties. For example, mass and inertia and joint, the position of joint and the length of link and the position of CON, something like that. So you can easily set up your dynamic simulation model. As I mentioned, we're gonna provide the CAD model. So just import the CAD model file to your simulation software and use it, and then use this property for your dynamic model. So you can simulate the dynamic something. Darwin is often platform we emphasize a lot of times. So which means you can modify the hardware. So this is one of the example. So we actually the robots will provide this kind of gripper, but what I want to say is not only this gripper, but also this style. If you want more degree of freedom for arm, you will insert this one more motor like that. So the arm has this will have this joint, so it will allow the arm to go somewhere more freely. So there's a big picture about hardware of Darwin. So if you have any question, feel free to ask.
Thank you, JK.